Wow, indeed. The era of video generation has begun. Sora has really catalyzed it, but there are many other players also racing to the top. But before we start losing our ability of knowing what's real and what's not, let's understand the AI that makes this possible. Today, I'll be doing a technical deep dive of Sora. We'll be covering everything from its training data to the model itself, space-time patches, its multimodal abilities, and its limitations. Whether you're just starting your journey into AI and ML, or you're a seasoned developer, this breakdown is designed for you. By the end, you'll have a clear understanding of how Sora works and why it's a game changer. So, let's get into it. And here we are. Let's dive right in. So this is today's agenda. First, we'll cover the dataset, how it was gathered and how it was labeled. Then we'll cover the model, including how it uses space-time patches, how it applies conditioning, and then piecing it all together. Then we'll discuss Sora's capabilities, particularly its multimodal ones. Lastly, we'll close it out with Sora's limitations and possible solutions for them too. These are the sources that I used. Today's technical breakdown is my best interpretation and consolidation of these available sources. First up is gathering a data set. We're training a video generator, so we gotta collect videos to train with. Lots and lots of them. And there's no limit to the type of videos that are being collected. We're talking all resolutions, all aspect ratios, all durations, 1 second, 1 minute, 1 hour. Therefore, that also includes images. Images are technically a video of 1 frame. So overall, in your dataset collection, you're going to have videos and images of all shapes and sizes and resolutions. Now, that's a lot of variety, and not all models are going to be able to handle that. In fact, what most video generators before Sora have done is crop their video data to certain specifications to keep them of uniform size. A little crop there, a little trim there. It sounds harmless enough, but as we're going to see in a moment, this has big implications down the road. Sora, on the other hand, decided to preserve the native settings of the video data during training. Sora is apparently the first model to do so. And what's the impact of this? Well, by choosing to not crop the training data, the model produced videos that didn't appear cropped. So for the same prompt of a scuba diver fed to Sora and other models, Sora shows her whole face, arms, and legs swimming, like as if she had recorded it herself. Other models, however, you get a partial view of things. The model was fed cropped videos, and it produces cropped videos. In the wise words of someone, you are what you eat. So yeah, model design matters, and in this case, the results show improved composition and framing. Another benefit of working with data of such diverse dimensions is that you adopt approaches that are more general than specific. This means, because your model can create both small and large videos, the Sora research team can choose to generate only small videos at low resolution during testing to allow for faster testing iterations, to experiment and change directions faster. In the example here, this small one is 3 times as small as the larger one here. So imagine the impact of this in real life. 1 month of testing versus 3 months of testing. And in this fast-moving race for AI domination, every minute counts. All right, we've collected videos, and now we need to give the videos some labels. And since Sora is a text-to-video generator, we need to generate some text that describe the videos, aka captions. Doing it by hand, all 1 million and more samples with humans would take forever. So you employ the use of a video captioning model to automate most of it. You feed in a video to the video captioning model, and it produces captions that describe that video. This model will focus on making the captions as descriptive as possible. So it'll describe things such as the objects, the surrounding, the environment, the visible text, the style of the video, any coloration, any events or actions happening within the video, and the overall mood. All right, now to the exciting part, the model and how it was designed. So there's obviously going to be a lot of components to Sora, so I'm going to tackle it in smaller chunks first and then piece it all together at the end. The first focus is on training the model in the pixel space, meaning a video is still a video made out of pixels. This here is one video with multiple frames, and you have that same video on the other end of this as well. So that same video is being fed as an input to the model and spit back out as an output. Now, why would we have it set up so that they're just spitting back out what we fed in? The intent here is to train an encoder and a decoder, where the encoder can encode the video into a lower dimensional space, retain just the important information, and then decode it back into its original components in the pixel space. The encoder is also called a compressor or a compression network. because it compresses the video into a lower dimensional representation. We call this the latent representation because it lives in the latent space. Sometimes it's also called the feature representation or embedding, but basically it's a representation of the input object, whether it be images, videos, text, audio, whatever it may be, into a simple numerical representation, because that's the best format that machines operate in, and therefore these models too. So yeah, at the highest level, you're training an encoder that can take a video into latent space, and then a decoder that can bring it back into pixel space. Now let's go into the pixel space and check out what's going on there. We're still in the training phase to still train the models that make up Sora. In the latent space, we have latent representations marked by the red grid boxes. We're starting with a latent representation on one end and finishing with a latent representation on the other end. And the intent is to train the diffusion transformer model in between them. That's a lot of words, so let's break it down. Diffusion is the process of gradually, iteratively adding noise to something until it looks just like noise. The goal is to train a model that can decipher the noise of the input and spit back out the legitimate contents of it. Diffusion has been a common method in generating images, and now it's being applied to videos as well. Transformers is a type of architecture that we've seen with the popularity of LLMs, but they also do well for vision domains like images and videos. They're great for training with large-scale data sets, which is what you need when you want to develop a highly capable model. Transformers are also great for handling long-range dependencies. So in the case of LLMs, that would be understanding a piece of text that is many paragraphs long. In the case of Sora, that would be understanding a video with many frames long. The transformers and their self-attention mechanism is going to help maintain that visual coherency from one scene to the next. One key aspect that I haven't mentioned yet is patchification. It happens to the latent object before it's passed into the diffusion transformer model, and to the original video before it's being passed into the encoder. So what is patchification? Basically, patchification is slicing an image or a video into smaller chunks, smaller patches, and then rearranging it into a sequence. There's two types of patchification: spatial patchification and spatial temporal patchification. In spatial patchification, the patches capture just the space aspect of the content. You have a video with many frames to it, each frame being treated independently from one another. Select just a couple of those frames, and then split the selected frames into a grid of patches, and then arrange it into a sequence, and that's what you feed into the network. Each yellow chunk here and each red chunk here is one patch. And here, since the frames are being treated independently from one another, the element of time has been neglected. Spatial temporal patchification, on the other hand, carves a patch in space and time. You can see here how all the frames are being retained, which means the element of time is being respected and accounted for. And by capturing dimensions in space and time, you're thus allowing the patches to retain all that dynamic information from the video. You'll then take these 3D patches and then arrange it into the sequence. And even though the sequence is long vertically, it's still going to be a three-dimensional element. So what this patchification does here is create space-time patches. And this patchification is part of the data pre-processing that happens in pixel space. So right before the video is passed to the encoder, it'll be converted to space-time patches. Some other things I'll add is the input videos may be a variable size, but the patches are a fixed size. The patchified output will therefore also have variable dimensions. So for that, you use a method called patch and pack, which handles the packing of multiple patches into the same size by using some padding. There's also the option of dropping tokens during the patchification, basically making the data more sparse. Lighter amounts of data means more efficiency. On the other hand, if token dropping is not done, then you get to keep all that fine-grained detail. And fine-grained details is something that matters for generating videos of high quality. So while other models might have opted to drop tokens for efficiency purposes, Sora might have elected to keep all of them because they can probably afford to do so. The other place that patchification happens is in the latent space. The latent representation of the video is still a three-dimensional object, and so the idea of patchification can still be applied, particularly spatial temporal patchification. The patches will again capture content over space and over multiple frames. So in the end, you'll have what's called is space-time latent patches. Note that patchification happens on the way in, and reshaping happens on the way out to return back to the same dimensions it started with. All right, next component is conditioning. So far, we've only talked about processing and training with video data, but again, Sora is a text to video generator. So how does the text prompt become involved in this process? Well, the user provides a text prompt of what they would like to see in the video. This gets passed to an LLM like GPT-4. The LLM will then augment that prompt to fill in more details needed for Sora, like describing the appearance of the object, providing more details about the surrounding and environment, specifying the style of the video, and indicating what actions or events might occur. That upsampled prompt is then passed to a model called Clip. Clip then produces a latent representation of the prompt, and that latent representation can then be passed to the diffusion transformer model. As a quick refresher on Clip, it's a model by OpenAI, and it's an encoder for both language and vision. It can take either text or images and create a mutual embedding for them that the other domain would understand. In other words, a picture of a dog and a text describing a dog would both be mapped into a similar embedding. So that's what Clip does, and it's frequently used in multi-modal generation frameworks like DALL-E and now Sora. So yeah, the text prompt that the user provides acts as a guide to the model in determining what the generated video should contain. And remember how I said that Clip is a dual encoder? Well, that means you can also feed in images and videos as a prompt, and that will also guide the video that Sora generates. So that's a lot of different type of input, multimodal inputs that Sora can receive, and we'll touch on that more once we get to the capability section. But firstly, you might be wondering what's an example of an augmented prompt, and for that, I have a really interesting example for you. So perhaps this video here looks familiar to you. It's actually from the Sora landing page. And as I was looking for an example for the augmented prompt for y'all, I decided to look at the prompt provided here. An alien blending in naturally in New York City, paranoia thriller style, 35mm film. Rather short, so I decided to pass it into ChatGPT and have it augment it for me with more details. It reads, "The alien, disguised as a human, wears a trench coat and a hat, faint glowing eyes, crowds of people walking past, yellow cabs speeding by." That is exactly this video here. This prompt that was generated by ChatGPT is describing the video that is generated by Sora. These are two supposedly separate platforms, but what this shows to you is two things: that ChatGPT and Sora use the same mutual LLM to augment its prompts. It's too rare of a coincidence that ChatGPT created the same augment as the video that Sora created for that short prompt. So yeah, ChatGPT and Sora, they're using that same LLM for prompt augmentation, which is fine. They're both from OpenAI after all, and now they're just sharing resources, reusing them. This is perfectly fine. But the other thing that this reveals is if ChatGPT is generating the same augmentation when I prompt it, and also the same augmentation when somebody else prompted it, that means that the model was instruction tuned a little too hard. It memorized the alien to trench coat and yellow cabs example a little too hard. So yeah, really interesting example that I uncovered there that I wanted to share with y'all. Now putting it all together, this is how the training phase would look. You start with one of the videos that you collected, put it through spatial temporal patchification, then pass it to the encoder for it to compress it into a latent representation. You apply the diffusion process onto the latent representation to get this noisy latent representation, which you will then pass into patchification again before it's passed into the diffusion transformer model. This model will then separate the noise from the clean latent representation, which will then get reshaped before it's passed into the decoder. The output from the decoder will then get reshaped back into a video again. The video at the end should then match the video at the beginning as closely as possible. You do that over and over again for millions of videos, and by the end of it, you have these 3 models that are trained. Now for the inference phase, you keep just 2 of the models, the diffusion transformer model and the decoder. From there, you append onto it the conditioning using the user's text prompt, image prompt, video prompt, what have you. Any combination of these will then produce a latent representation of the prompt that will be fed into the diffusion transformer model, along with a latent representation of a video that is randomly sampled from the latent space. With these 2 latent representations passed into the model does its thing, separating the noise and generating a latent according to the prompt. This latent video then gets decoded into pixel space into a video format that humans can perceive. And voila, that's how Sora was made and how it runs. I'm just going to reposition the workflow so that it looks a little bit nicer. I'm a little picky like that. So if you're gonna screenshot this, use this slide instead. Or better yet, share the video. So what I've presented to you today is a high-level overview of Sora's framework while still elaborating on the technical details. The flow was hopefully easy to follow from left to right. I'm also gonna share with you an alternative way of illustrating the framework. This is a diagram from one of the papers. It conveys the same information, but in a really compartmentalized way. I find it a little harder to follow, but I do like how they split their layout into the pixel space, latent space, and conditioning. Now, for those interested in details of the model's architecture, like the layers and such, that is not publicly available information, so I can't speak to that necessarily. The only thing that can be done is speculation. So for that, I'll share this diagram of an architecture for diffusion transformers and vision transformers. There is a strong likelihood of Sora using some variation of this. We see the familiar components, like the self-attention mechanism, which is great for focusing on the most relevant parts of the data and for capturing dependencies over a long range too. We see some layer normalizations, multi-layer perceptrons, feed-forward networks, and over here we see some convolutions along with some skip connections, as well as our familiar self-attention mechanism. All right, so we've covered how Sora was designed and trained. What can it do exactly? It's called a text-to-video generator, but really it can do so much more than that. We're going to talk about the multimodality and versatility of Sora. It's a lot, so we'll run through them quickly. First use case is obviously going from text to video. Here's that same example of the alien as we had discussed. Next use case is a text prompt and an image, like the one here and the image given here. Then Sora will animate this image according to the text here. So they're talking about a tidal wave peaks and begins to crash. Two surfers skillfully navigate the wave. And we see a video depicting just that, building off of the image that was provided as a initialization point. Next use case is we can feed Sora a video, and for that same video, Sora can extend it by either before or extend it after. Basically elongate it in both directions. They've named this capability as one of their editing tools called Recut. Next use case, we can again feed Sora a video, and for that same video, Sora can convert it into a looped video, either taking a sub-segment of the video and looping that, or elongating the video as needed to complete a loop. And the video would be elongated with that extend feature as we just saw. This looping capability is also one of their editing tools called Loop. Another use case for Sora is feeding in a video and an editing prompt. So this here is the original video you want to work off of. This text here describes how you would like the style of the video to be changed, particularly to be shot in black and white with deeper shadows and a vintage cinematic vibe. And that is what Sora will do. This here is that same video of the mammoth and the rhinoceros, but the style of the video has been modified to be black and white and more old style cinematic. This capability is also one of their editing tools called styled presets. The last use case that we have for today is you can feed Sora 2 videos and Sora will return to you one video that is the blending of both videos. So here in this example, we have snowflakes falling as one video input and flower petals falling as another video input. And the result of that is, as you can see, a blending of snowflakes and flower petals falling together. This is also one of their editing tools called Blend. So as we can see from all those use cases, Sora is incredibly multimodal, being able to handle a diverse combination of inputs. To further describe Sora's capabilities, Sora exhibits 3D consistency, despite lacking explicit 3D modeling. So even when the camera moves around an object, the object maintains its form. Sora demonstrates object permanence, which for example includes when an object gets occluded for a few frames, the object can still re-emerge in the same form as before the occlusion. Sora demonstrates long-range coherence. As an example, that includes when Sora cuts from one scene to another scene, the same object can still be seen in both scenes. Sora can simulate interactions with the world. So in this example here, the man is eating the burger and the burger loses a chunk of it. This ability here is also pretty crazy. Sora can generate digital worlds like Minecraft and control the player and generate the world according to how the player plays. Sora is also the first vision model to exhibit confirmed emergent abilities. Like ChatGPT have already been confirming emergent capabilities for a good while now, but no vision model has up until now. Okay, so those are a lot of capabilities that we just covered. So what are its limitations? So in the context of Sora striving to be a world simulator, these are some of the challenges that it faces, including physical realism. Sora doesn't always depict the physics of the scenario correctly. As an example, this broken glass and this man running backwards on a treadmill. And much like large language models, large vision models also suffer from hallucinations, sometimes inserting in irrelevant characters and objects into the video. And Sora also exhibits limited semantic precision. Now, this is a term that I've just coined myself, and I'm pretty excited about it. And what I mean with that is Sora might not be able to follow all of the user's instructions. This includes semantic aspects such as temporal, positioning, events, appearance. So if the user asks Sora to place the ball on the left side of the room instead of the right side, Sora might not be able to comply with the positioning request. If the user describes to Sora, first this happened, then that happened, then that happened, Sora might not be able to follow the temporal flow of all that. If the user asks Sora to make the shirt red and the hair blue, essentially changing the appearance of an object, Sora might not be able to comply or has limited abilities to comply. If the user requests specific action details from Sora, like keep the hair clip open, floating in space, but Sora only presents it as closed in space. So yeah, Sora exhibiting limited semantic precision. Now that's a lot of issues, and one approach to addressing them is throwing in more training data and more compute. And comparing Sora from where it is today to when it was first announced in February, it has undergone a huge improvement, thanks to more training data and more compute. This is what worked for LLMs, and now it's working for vision models too. However, vision models are also subject to scaling laws, meaning at some point, throwing in more data and more compute isn't going to get you the same improvements as before. The vision models, no matter how much data you throw at them, will start to have diminishing returns. Sounds like a pretty serious problem. You might wonder if there are solutions to this. From my humble opinion, I believe there are. I believe the solution to a lot of these limitations is physically based video generation. So that would be building from the ground up rather than from the top down, as I perceive Sora to be doing. There's a few companies building with this approach already, including World Labs and Genesis, and I'm very confident that their approach is the more robust one. So I'm really excited to see what they have in store for us in 2025. Who knows, 2025 could be the year that other AI companies catch up to OpenAI. And lastly is evaluations. That is a required step in any machine learning pipeline. For vision models, both quantitative evaluations and qualitative evaluations are necessary. So for that, I would direct you to my previous video, shameless plug, where I do a qualitative evaluation of the videos that Sora has produced. I go through individual examples in more detail, and I discuss the good and the bad. I provide you an analysis of the video through my lens as a machine learning engineer, basically giving you insight into how a machine learning engineer sees and thinks about these vision examples. And that's all for today's breakdown. We covered a lot, including how the dataset was gathered, how it was labeled, an overview of the model, including technical details like the space-time patches, how it gets conditioned, and then piecing it all together. We talked about Sora's many capabilities, its limitations. I provided references for an evaluation of Sora. If you made it all this way, kudos to you. Thank you so much for watching. I appreciate your attention, and I hope you were able to learn something from today's technical breakdown of Sora. See you next time.